Hello, everyone. Thanks for attending my talk. The title of this talk is Analysis of Decarbonization Pathways and Flexibility Requirements in the Chilean Electric Power System. My name is Álvaro Lorca. I'm a assistant professor of electrical engineering and industrial systems engineering at Pontificia Universidad Católica de Chile. And this is joint work with Felipe Verástegui, Cristian Villalobos, Nicolás Lobos, Matías Negrete, and Daniel Olivares. Okay. So the context of this talk is basically, here's a little outline, introduction, methodology, results, conclusion, basically. And the context of this talk is what we're experiencing right now as a world with climate change and really ever more pressure on our energy systems. Okay, so many power systems across the world are starting decarbonization processes. Okay? In particular, in Chile, we already have a compromise for removing all coal electric power generation before 2040. Okay, and other countries are raising similar goals. And this sets a very interesting setting and a very challenging setting for the power system, because as we remove coal, we want to have more and more renewable power. Okay, and in Chile we really have very nice natural conditions for both wind and solar power. So the main problem, which is basically what's in this slide, is that as we remove this controllable and dispatchable resources, which is coal, we start increasing the presence of variable renewable energy sources, which is basically wind and solar power. So this produces pressure on how we employ, on the flexibility requirements of the power system, and how we employ the flexible technologies, and what type of flexible technologies we need to deploy throughout time as we go along removing coal and increasing the presence of renewable sources. Okay, so this is basically the challenge we face in this study, and we try to analyze and understand in this study. Just a bit more of context. Today, we have about 40% of the generation mix coming from coal. Okay, so going from 40% to zero in 20 years is quite an important change in our system. So again, the concept is flexibility, and a key role is played by storage systems. Okay, not only batteries or even hydro resources, which we do have in Chile, but also this beautiful technology, which is concentrated solar power. Okay, we are currently building in Chile, we're under construction, the CSP plant of our system. CSP stands for concentrated solar power. And this is a very nice technology where you can basically use solar power throughout the night and basically store power through thermal processes, okay, in a completely renewable way. Okay, so a little bit of our methods, models, and data in this study. Our main tool for studying this problem is using expansion planning models. Okay, so the basic idea of this model, of this type of models, and what we do in this study, is to look at the Chilean power system throughout a 20-year horizon, from 2020 to 2040. And we need to look both at the investments that will be carried out in these 20 years and the operational costs needed for satisfying all the demand from the power system, while satisfying various physical or operational constraints. Okay, so the idea is we want to minimize the total cost of investments plus operation, such that we satisfy demand and we meet a series of let's call it environmental or policy constraints, namely that coal has to go to zero in 2040 with some trajectory. Okay, and actually, as I mentioned before, we currently have a schedule for removal of coal, and this is at least the plan for the first 5 years, which removes about 25% of coal capacities, okay, in megawatts. And we also study three scenarios, okay, which is the current compromise, Chilean compromise of completely removing coal by 2040, which we call D40 or decarbonization by 2040. And we also look at this D35 here and D30, which is decarbonization of coal, only of the coal part, by 2035 and 2030 respectively. Okay. So this is a little bit of what I mentioned. We employ 6 periods of 4 years in this case. So we plan until 2044 just to have additional 4 years to avoid end of the horizon effects. So as I mentioned, the idea is to decide where, when, and which technology capacity investments to carry out for this horizon, also looking at operations. And we built on previous work by ourselves. This is Meda et al. 2019, also Maluenda et al. 2018, and also from this other paper, which is Hua and Baltic from 2018, okay, which we use to improve the modeling of our operational representation of the system, including some, let's call it, flavor of unit commitment. It's really hard to capture a full unit commitment model in a planning problem, okay? However, there's some techniques that allow us to have a reasonable relaxation of such constraints, which is a key asset for understanding the flexibility of the system a little better. So this is our representation of the Chilean system with 20 zones, okay, and about 20 or 23 transmission corridors for power. We also have a quite detailed representation of the hydro network with hydro corridors, reservoirs, and so on, looking at dam hydropower generation and also run-of-river hydropower generation. And our approach for understanding the flexibility of the system and for representing the operations of the power network is to use, in this case, 6 representative days. So the idea is each year or each planning period, a planning period has 4 years, as we mentioned before. Each of them is represented by 6 representative days. The information in each of these days is a wind power signal for every zone, solar power signal for every zone, load power signal for every zone, and also a hydro availability in wherever there is hydro. Okay, so all of this goes into selecting the 6 representative days. We could use more days, of course, which would give us a better operational representation, but we've seen that this is good enough to capture the main effects on the investment decisions. Okay. And as I mentioned, there's some flexibility constraints from Hua et al. 2018, which allow us to capture some unit commitment effects in an approximated way. There's a lot of other data that goes in, and our environment for modeling this is using Python, Pyomo, and the switch model. Okay, which you can Google, and it's basically a set of a basis for planning models. Okay, regarding the results, and I only have 6 minutes left. These are the investment or the cost decomposition. Okay, the cost structure for the overall planning until 2040 in the 3 scenarios studied. Okay, so as you can see, total cost is roughly about 10% or a little less smaller in D40 as compared to D30. Call that D30 has a tight constraint for removing coal generation by 2030, whereas here coal is removed by 2040. So naturally, you have more constraints here. It's a higher cost overall. I can't go over all details, but what this table tells us is that D30 is basically carrying out a lot of investments, much more investments than D40, because of this tight deadline for coal generation, which is 10 years earlier than D40. This is the capacity mix throughout the whole planning horizon. The final capacity mix is not too different, but the trajectory is a little different, as I mentioned before. In D30, you have to carry out a lot of investments early in the planning horizon, as expected. Again, this is actually the same idea here. Some interesting things. This is actually the generation mix now, not capacity, but generation in terms of energy, is that CSP plays a very important role in all of our scenarios. And of course, CSP comes in a lot before in D30 than in D40. Okay. As I mentioned, the final generation mix is not too different for the three scenarios, and there's some key takeaways here. This is the current mix in 2020, which is very similar to what we're seeing these days in our system, and this is the 2040 mix. Okay, so we see a lot of CSP, more than a fourth of the power generation, much more wind than today, a little more photovoltaic than today, an important role of gas, okay, an important role of hydro dams, but much less than before, and a more important role of hydro river, okay, run-of-river hydro generation. This is the 6 representative days for 2020, and these are the 6 representative days for 2040, where we see 24-hour horizon for each of these days and the role that each technology is playing throughout the day. Okay. This is what CSP does throughout the day. I don't have time for details here. These are emissions. Of course, emissions go down a lot. Emissions today are mainly from coal generation. If you assume that there's not too much gas, the usage of gas these days depends on the prices. So we do see some gas today in practice. It's not represented here because of the cost structure we employed, but we see that in 2040, basically all of the CO2 emissions come from natural gas. Just some conclusions. Decarbonization is a key process under the current climate crisis, okay? And we need this to enable a low carbon economy, or hopefully zero carbon economy sooner than later. This process creates key flexibility challenges in power system. As we remove coal and we increase wind and solar, we need to take good care of flexibility in the power system. The use of planning models may provide insight in operational issues to be expected and the role of new technologies in this transition. That's basically a summary. Now, some conclusions. Under all scenarios, there will be a lot of variable renewable energy in our system, and flexible generation technologies such as CSP. I didn't mention batteries too much, but we do see some role of batteries, but much more important role from CSP, okay, for us flexibility providers, and also gas as a flexibility provider, natural gas. Accelerated decarbonization processes will naturally present higher costs for the overall system and thus for society. But the benefits of this might significantly be, more important than those costs. So that's something that every country needs to, bring into the equation and see how fast should we remove CO2 emissions. And finally, the increase in CO2 emissions in final periods should be addressed through a more comprehensive policy. So removing that percentage of gas that we see in 2040 will require a more important role from these flexible renewable technologies, say CSP, batteries, and even hydro. Okay, and that's something that can be done. We see that gas is not playing a huge role by 2040. So bringing the system to a zero emission power system might not be too far away from 2040. And this is particularly important if we want to decarbonize the rest of the economy, or the rest of the energy system, which is not electric. And we will need to electrify a lot of those consumptions of energy that are not electric, say cars and so on. Okay. The effective placement of flexible resources is a key point. I didn't have time to go over where these technologies are installed, but this is a key thing in Chile, where we have a lot of hydro in the south and a lot of good solar resource in the north. So it's really important where you install flexible assets. Okay, and some more comments here along the same line. So that's my presentation for today. This is the references we employed, and thanks so much for your attention. Feel free to get in touch if you want to see the papers we're developing along this line. Thank you.